Hey everybody, welcome back. We're going to look at 8.3, which is how do we evaluate logs. So we're going to be using our calculator in this section, so make sure that you have your calculator, and they all should have a LOG button on it. Now let's go through this. So first, right off the bat, it says express each of the following in logarithm form or exponential form. So this is what we learned in 8.1. So we should know that log 5 of 25 is equal to 2. Right? That's the exponent. You could have written it the other way, is equal to 2. Doesn't really matter. Same idea. Same goes for the next one. So we want to write that in exponential form. Or that is in exponential form. 4 to the power of negative 3. We want to write it in log form. So the exponent is negative 3. So negative 3 is equal to log of the base. That's 4. 1 over 64. Right, there's no variables here. We're just rewriting it. Next one. This one's in log form. We want to write it in exponential form. So we have our base 3 and our exponent 3. So this says 3 to the power of 3 is equal to 27. And finally, the last one over here, that's written in log form. We want to write in exponential form. Well, in log form, 5 is the base to the power of negative 3 is equal to 1 over 125. Right? That's just our a, y, and x. Right? We have our y value, our x value, and our a value, our base. Remember, when you write them, it's a to the power of y is equal to x, if you forgot. And that's true for all of those logs. So if I want to evaluate these, how do I go about that? Well, a few different ways. I'm going to show you one to start, and then show you another in a minute. So first one that we have here, log 381. Basically that says, well, let's suppose this is equal to y. That's saying 3 to the power of y is equal to 81. Well, I know 81 can be written as a base of 4. So therefore, y is equal to 4. Being able to write them as the same base and equating the exponents is going to be an important skill later on. That's why I did it here. You might have looked at it right away and said, well, I learned way back in grade 11 that I can evaluate log 381, and I got 4. That's fine. But when we're actually solving them later on, you're going to want to be able to write equal bases on both sides. So let's try next one here. Log 7 is equal to 1. So we're saying 7 to the power of y is equal to 1. So you might look at it and say, I don't really know. Well, remember, anything raised to the exponent of 0 is 1. 7 to the power of 0 is 1. So y must be equal to 0 in this case. And last one over here. 1 over 2 to the power of, we'll call it y, is equal to 1 over 32. So one thing that you might remember about exponents is that they apply to both the top and the bottom. So really it's 1 over 2y is equal to 1 over 32. And we're trying to find out, well, what is the exponent that I could have on 2 that would give us 32? So really it's like 1 over 2y is equal to 1 over 2. You might say, well, what is the value of the exponents? You maybe use trial and error. Maybe you say, well, 1 2 is 2, 2 2s is 4, 3 2s is 8, 4 2s is 16, and 5 2s is 32. And you say, well, 2 to the power of 5, that's fine as well. So y is equal to 5. Now, this is where we get into parts where we can use our calculator a little bit. Our calculator only recognizes common logarithms. If there is a value for a in the expression log ax, the base is understood to be 10. So, for example, this one here, if we just write log x, we're assuming that the base, that there's a little 10 on here. Just like a square root, we assume that there's a 2 out front. For logs, we assume it's a base 10 unless we're told otherwise. That's called the common logarithm. Logarithms with base 10 are called common logarithms. So for example, these ones here, it's like writing log 10 100 or log 10 1 over 1,000. And maybe log 10, 57. Those are just called common logarithms. That's what your calculator recognizes. So when you look at your calculator and hit the number log, you would not be able to put in a base for it. It's just assume that it's a common logarithm. So you can try your calculator and put those values in that we have. So log 100, when you do that, you should get 2. Why? Because 10 to the power of 2 is 100. Try the next one. If you put that into your calculator, you should get 10 to the power of negative 3. Which means that we should get negative 3. Because 10 to the power of negative 3 is equal to 1 over 110. Or 1 over 1,000. And finally, the last one. You might say, well, I'm not sure because 10 to the power of something is 57. And you might say, well, if I'm trying to solve that one, it's kind of difficult. I know it's between 1 and 2 because 10 to the power of 1 is 10. 10 to the power of 2 is 100. It's a little bit more than that. But we have our calculator. When I put in my calculator log 57, we get 1.7558, so 1.76 about. Maybe rounded that one. Important properties of logs. So, if we have log A1 is equal to 0, any exponent of 0 results in a value of 1. Why? Because if this is 0, this is always going to be 1. Because essentially, this is saying a to the power of 0 is equal to 1. And that makes sense. Next one. If we have something like this, log a, so if we have the same base, and our argument has a base of a, that just means x is equal to x. And you might say, well, why is that true? Well, if I took this and I wrote it in exponential form, ax, a to the power of x is equal to the argument, a to the power of x. Right, they're just the same. So anything, if we have log of a base and our argument has that same base, well, the answer is whatever the exponent is. And we'll look at some examples of that. And finally, the last one that we have here, if we have a raised to the power of log ax, that just means x is equal to x. That's our answer, whatever's the part that's left. Right? If I'm ever given this, the answer is whatever's on the end. Why is that true? Well, this here is technically written in exponential form because it's a to the power of this, has a log in it. But I'm going to take that exponential form and I'm going to write it in terms of logarithm form. So logarithm form of this, so let's suppose this was a y is equal to x, where y is that log ax. If I wrote that in exponential form, you know that that's going to be log a x is equal to y. So if I'm doing it with this one here, it'd be log ax is equal to log ax. That means they're exactly the same. So we'll look at an example like that. So if you have something like, let's suppose we have 7 to the power of log 7, 12. That's equal to just 12, whatever this is. Now we'll look at some examples of that. Oops. So simple exponential equations can be evaluated using a variety of strategies. Express both sides in exponential form with a common base and equate the exponents like I've been doing. General idea is get them to have like b to the power of x, b to the power of c, so that b is equal to c. That's one way. Or we can rewrite the equation in logarithm form and simplify. Usually one is better than the other. So let's look at what we have here. Y is equal to log 410. Well, that's not a common log 464, not 10. But it does not have a base of 10, so I can't put that into my calculator. So if I want to solve this one, I'm going to have to put it in exponential form because 4 to the power of y is equal to 64. And then we might say, well, 4 to the power of y is equal to 64. Well, 64 is 4 to the power of 3. So the exponents are y is equal to 3. Right? We're just equating these exponents here, y and 3. They must be equal to each other because they have the same base. We'll keep going here. Next one, if I write in exponential form, it'll be 3 to the power of y is equal to 1 over 27. 3 to the power of y is equal to, well, that 27 is on the bottom, so when it comes up, the exponent's going to be negative. And 3 to the power of 3 is 27, so it's got to be negative 3. So if I'm equating those exponents because they have the same base now, y is equal to negative 3. All right, let's keep going here. Now this one here has parts that we can evaluate. I can square root 25. That's just equal to 5. So I'm going to simplify that first. So when I write this in exponential form, I'm going to have the base, right? That's the small number that's with log. 5 to the power of y is equal to 5. Now when I look at that, there's no exponent on 5, but we know that there's always an exponent of 1 if nothing's there. So we have y is equal to 1. Equate those exponents together. Probably getting the hang of it now. Next one, 4 to the power of y is equal to 1 over 16. 4 to the power of y is equal to, well, 16 is on the bottom. 4 squared is 16. So since it's on the bottom, it's got to be negative 2. Y is equal to negative 2. Now this one's a little bit different. Our unknown is here, but that doesn't mean we can't solve it. So right now, x is not isolated. But if I put in exponential form, 4 to the power of 2 is equal to x. Now it's isolated. I can solve that left side. 4 squared, 16 is equal to x. Sixth one here on the right, if I put in exponential form, 2 to the power of y is equal to negative 4. So you might look at that and say, how do I get negative 4 from 2? Well, as that y value gets bigger, if I go from 1 to 2 to 3 to 4 to 5, the number's getting a bigger positive. What happens when I go the opposite way? 2 to the power of 0, well, that's 1. How about 2 to the power of negative 1? Well, that's a half. So we're not negative 4 quite yet. Whoops. 2 to the power of negative 2, what happens? Well, that's 1 over 4. So we're not getting there. So one thing about exponents, when you have a positive base, you can never get a negative answer. Even if I have negative 100, that will be 1 over 2 to the power of 100. That's still not negative to get me negative 4. So y is undefined. There is no y value in this case. No exponent I can put on 2 will result in negative 4. All right, keep going along here. Remember this rule, we have 1. So I know that that x is going to have to be 0. That was our first rule that we talked about. But let's just show that. If I put this in exponential form, 7 to the power of x is equal to 1. Well, I know that x has to be 0 because anything to the raised to the exponent of 0 is 1. This here was our third rule that we talked about above. Remember, we have log 3, and I said, well, the result is going to be 2. And why is that true? Well, I'm going to put this in exponential form. 3 to the power of x is equal to the argument, which is 3 to the power of 2. So x is equal to 2. Equate those exponents together. And we can keep going here. 4 to the power of x is equal to 8. And you might say, well, how do I get 4 to the power of x is equal to 8? In this section, it says to use trial and error if we do not have nice values. So we would put things like 4 to the power of, I know it's going to be between 1 and 2 because 4 to the power of 1 is 4. 4 to the power of 2 is 16, so it's somewhere in there. But we'd say, well, 1.5, for example. And that one gives me 4 to the power of 1.5. Whoops, 4 to the power of x, whoops, is equal to 4 to the power of 1.5. So that would be 8. Now you might say, how do you get 1.5? Well, that was just trial and error for now. I'm going to be showing you a way that you can evaluate them. And I'll mention it here just quickly in case you're curious. basically what we're going to get to is that we can take something like this, and if I want to write them as common logarithms, I would write them as log 8 divided by log 4. That's how I can evaluate those. So log of the argument divided by log of that base will give me the same value. That should give me that 1.5. And that's going to be in the next section. We're going to go over why that's true. But for now, that's kind of how we would evaluate those as common logarithms. Just want to introduce it. And this section tells us use trial and error for now. The last one that we have over here on the right, if you remember, I told you one of our rules was if we have a base raised to a log of that same base, the answer is just going to be 20. And if we say, why is that true? Well, this is written in exponential form technically. So if I was to write it in log form, I would say log of 6, so right, the base that we have, y, the exponent, log 6 of 20, right? This was the exponent up here. So if I look at these ones and I say, well, what's the same on the left and the right side? Well, I have y here and I have 20 here. So y must be equal to 20. And finally, we kind of talked about it earlier, but the trial and error questions when we do not have a nice whole number. So for example, log 2, 81, what is that? Well, it's saying, well, 2 to the power of y is equal to 81. We could use trial and error to try to find out what it's going to be. So 2 to the power, and we keep trying different numbers. But I told you earlier that if we want to evaluate something like this, one way that we can evaluate that would be log 81 over log 2. I kind of gave you that shortcut. In the next section, I'm going to explain why that's true. But when you put that into your calculator, whether you use trial and error or not, just trying to limit what you're doing, you should get the answer of 6.34. Right? 2 to the power of 6.34 will give me something close to 81. It's been rounded, but it's close to 81 using that trial and error to 2 decimal places. And the last one over here, if I was to evaluate it, I might say, well, let's put it in exponential form. 5 to the power of y is equal to 45. And if I look at this, I know the answer is going to be somewhere between 2 and 3. Because 5 to the power of 2 is 25. 5 to the power of 3 is 125. But I said, well, we can evaluate these ones by doing log 47 divided by log 5. Right, you could use trial and error if you want. 5 to the power of, try a bunch of different numbers, try to get 45. But that shortcut that I showed you that I'm going to be explaining in the next section, if I do that, we get 2.39. So 5 to the power of 2.39 is about 45. So y is equal to 2.39. And that's using that rule up the top. That's just getting common logs for both, because technically that's log 1047 divided by log 1005. That will give me that 2.39. And as I said, I'm going to talk about that in the next section, but that's how we can evaluate these.